The next thing that happened was that some scientists were not very happy because, again, this was a time during when light was believed to be a particle. And so the next sort of advancement in physics was this thing called the photoelectric effect. And so if you remember from term two, you did something called the photovoltaic cells, which essentially was a very fancy word for solar panels. And so what the photoelectric effect is basically it basically tells us how solar panels actually work, or how photovoltaic cells actually work. And essentially, this is what's happening. So we have some light, and over here there is some metal, and when this light hits the metal, so first of all, we have the circuit, and this circuit's been cut up in the middle, and in the middle we have some sort of vacuum. It's called a cathode ray tube. So in the middle we have this thing called, I'll just quickly write it down, a cathode ray tube, something like that. Yeah, a cathode ray tube. And when the light hits the electrons, essentially the electrons get displaced, and the electrons are going to travel to the anode, and it's going to create a circuit. So electrons go here, come here, and we have this circuit being created. First of all, for anyone who's doing chem, anode and cathode over here is not the same as the chem anode and cathode. So please don't confuse the two. The anode and cathode in physics has no connection to the chemistry one. So please don't confuse the two. In this case, in photoelectric effect, the anode is positive. The reason the anode is positive is because the electrons have to go from here, and the electrons have to travel from this left side, and they have to go to the right-hand side, and that can only happen if the anode is positive and the cathode is negative. And again, in chem, it will be the other way around. So that's why you don't want to mix up chem and physics. Yeah, so cool. And just a bit more terminology for this stuff. Yeah, so we have a metal tube at the cathode, which is over here. We have some metal. We have a monochromatic light. So monochromatic meaning a singular wavelength. You can have multiple wavelengths. It's just that, just to keep things simple for VCE, we just assume that the light is going to be monochromatic, and it's shone onto the cathode. We have an ammeter to detect how much current is being created, because again, when the light shines on the metal, it's going to complete the circuit and it's going to create some sort of current. And then we have this thing called a variable voltage, and basically it's just this little thing over here. It's like a battery, and it's like a power source, and you can pretty much change the amount of voltage that this power source is producing. And yeah, this thing called forward potential and reverse potential. Forward potential is essentially when the current is working and the light is actually creating current. So the forward potential would work in this direction. So the electrons are going from cathode to anode, as they should be doing. The reverse potential is the opposite. So the reverse potential travels in this direction. And this is controlled by this variable voltage. And I'll show you why that's important. So the thing was, when the light was getting shone onto the electrons were getting ejected. So you can imagine we have electrons here, and all of these electrons, they're getting ejected. What the scientists wanted to calculate was how much energy do these electrons have. Yeah, these electrons called photoelectrons. Photoelectrons are basically a fancy word for saying fancy word. Why can't I write? Oh, yeah, fancy word for saying electrons ejected by ejected by light. And so these electrons, they are traveling from here to here, and because they're traveling, they obviously have a velocity and they have some sort of energy. What we wanted to calculate was how much energy does the electron have. But the thing is, it's a bit difficult to calculate how much energy an electron has. So what the scientists did is, all right, so you can imagine this. So let's say we have some force. Let's say we have a force in this direction of n newtons. We don't know how much force. We don't know how much force that is. But what you can do is you can apply a force in the opposite direction, and you can change the amount of force. So let's say you put 50 newtons of force. Say you put 50 newtons, and you put 100 newtons, and you put 200 newtons. What you want to find out is what amount of force is going to match this. What is going to match this amount, right? So what you would do, you would try out your push with different forces until the red and the green is going to cancel out. So let's say, for example, if this is 75, right, but you don't know it's 75, but let's say it is 75. So if you push with 75 newtons, these two things will cancel out. And then from that, you would know that the red line has exactly 75 newtons. And so that's basically what the scientists did. They used a reverse potential, and they shot, so the current of the photoelectrons is going to the right. It's going this way. It's going clockwise. But what the scientists did with reverse potential, they induced a current going in the opposite direction. So this is what they did. So they created a current going anti-clockwise. And what they did is that they changed the voltage until there was no current. Right? So if there's no current, that means the voltage, that the reverse potential is the same as the forward potential. So there's no current being formed. Because again, the electrons are being balanced out by the opposite force of the voltage. And so this is called the stopping voltage. So essentially, how much voltage do we need? How much voltage do we need so that there is no current being formed? And so this is how we can calculate how much energy the electron has. So from unit 3, we know that voltage, that work is equal to Q times V, where Q is your charge and V is your voltage. In this case, since the reverse potential is creating current in the opposite direction, the charge is equal to the charge of an electron. So this E would be 1.6 times 10 to the negative 19. So now you get this formula where work is equal to charge of an electron times the stopping voltage. And all of this is equal to kinetic energy. And this is something you've done in term 2, right? So since the electrons are being ejected with some sort of velocity, they obviously have kinetic energy. And the kinetic energy of the electron is now equal to E times V, where E times V is basically the stopping voltage going in the opposite direction. Right? So we want to cancel out the two forces until we get 0. And that's basically where this formula is derived from. Oh, and at this point, stopping voltage will stop even the fastest moving electrons. So you can imagine that these electrons, they're being shot to the other side. And the stopping voltage is exactly the amount that you need to stop every single electron. And so let's say the stopping voltage is 2 volts. Using exactly 2 volts, you can stop every single electron from going from here to there. And there's another unit to calculate energy, and it's a non-SI unit called the electron volt. And because you can see, if I go back, since we're multiplying everything by 1.6 times 10 to the negative 19 a lot, just to just to help out, we use a different unit called the electron volt. And the electron volt is how much electron volt is this. Okay, so electron volt is how much energy does an electron have if it's charged with 1 volt. So 1 coulomb of charge is accelerated through a potential difference once, it gains energy. When 1 electron is accelerated through potential difference of 1 volt, it gains 1 electron volt. So again, so we have W is equal to QV. The charge of the electron is 1.6 times 10 to the negative 19. The voltage is 1, in this case of electron volts. And all of this is equal to 1 electron volt. Yeah, sorry. Oh yeah, all this is equal to 1 electron volt. And if you want to convert between the two units, so let's say we have joules here, we have electron volts here. To go from joules to electron volts, you have to divide by, divide by 1.6 times 10 to the negative 19. And to go the other way around, it would be 1.6 times 1.6 times 1.6 times 10 to the negative 19. Yeah, hopefully that's right. So with this topic of photoelectric effect, your units can be given in either joules, or they can be given in electron volts. And your job is to convert between the two, depending on which is more feasible. Cool. So when this person, what is his name? What is his name? Right. So whatever scientist this person was who created the photoelectric effect, they found a few things. So what the guy did, right? So we have this light that's shining on the cathode. What he did, he swapped out the lights. He tried out different lights and saw what happened. What he thought was that every single light should be able to produce some current, right? So he thought that doesn't matter what light you use, it will create a current and it's going to displace the electrons. But that's not the case. That's not the case because of something called the threshold frequency. And threshold frequency is what I like to call like the get out of bed energy. Let's say that the threshold frequency is 100 joules. If your light has less than 100 joules, let's say if your light has 90 joules of energy, it doesn't matter how much light of 90 joules you put. The threshold frequency, since it's lower than the threshold frequency, there's going to be no electrons being emitted. So, yeah, because it's less than a threshold, it's not going to create any current. So, if you want to create current, you have to shine a light that has a greater frequency than the threshold frequency. So, you need light that has 120 joules of energy. The second thing he found out that increasing the intensity of the light increases the number of photons, which, as you'll see later on, will increase the current. And he saw that the photoelectrons were released immediately. And the reason this is shocking is because at the time, these were the predictions. So at the time, it was thought that every single frequency, according to their knowledge of light, it was assumed that every single frequency of light should be able to emit photoelectrons. So it doesn't matter what, so frequency is essentially the color of light. So they thought every single color of light should be able to produce photoelectrons. But that's not the case because according to the experiments, there was something called the threshold frequency. So the frequency of the light had to be greater than the threshold frequency, or there would be no photoelectrons being emitted. The second thing that was believed was that the intensity of a light, so intensity of light is basically the brightness of the light. That is your brightness. The intensity of the brightness of the light will impact the kinetic energy of the electrons. So if you were to increase the brightness, it was assumed that the electrons will travel faster and the electrons will have more energy. But that's not the case. What happened in actuality was that when they increased the intensity, the number of photoelectrons increased, which since you have more electrons, you're going to increase the current. So increasing the intensity will increase the current. And the last thing that was assumed was that the photoelectrons will take some time to have some time delay between turning on the light and actually seeing the photoelectrons. But in actuality, the photoelectrons were released instantly. And so these predictions, they were based off the wave model of light. So according to the wave model, all frequencies of light should have been able to emit photoelectrons. But they didn't. And these predictions, again, these are from the wave model. I'll have to go through these a bit quickly just because of time. So to explain this, Einstein came to the rescue, and what he said was that light can be modeled as this thing called discrete quantized packets of energy called photons. Or in other words, you can just imagine light to be just some, just imagine light to be tennis balls. Right, so you basically have a bunch of tennis balls that is hitting the electrons, and the energy of the tennis ball is going to the electrons, and the energy just gets transferred to the electrons. Yeah, and so what they found out, it was this equation. So energy is equal to h times f, where h is a constant of this value. And so what they found out is you can actually calculate the energy of light with this formula. So E equals hf. And which is why when we go back to our electromagnetic spectrum, gamma rays have the most energy because they have the highest frequency. And you can kind of see how that all is tying together. And this formula, E is equal to hc divided by wavelength, that just comes from the formula of C is equal to a wavelength times frequency. And then solving for frequency, you get frequency is equal to C divided by wavelength. Combining the two, you get this formula. Yeah, so it's the same. It's the same formula. And what's the other thing that Einstein found was something called a work function. And work function is the minimum amount of energy needed to release the electron. So, so each metal, there's a minimum amount of energy that you need for to displace the electrons. Yeah, so similar to the what is called threshold frequency. So there's a minimum amount of energy that you have to meet to actually get photocurrent. And so putting that all together, you get this. So the energy of the electrons being emitted is equal to h times f. So h times f, that is our light energy. This is and light energy. And this symbol, I don't know what it's called, but that is that's our work function. So the energy of the electrons is essentially light energy minus work function. And whatever remaining is the amount of energy you're going to have. So what you can do is you can sort of graph it. You can graph this. Essentially, it's just a linear line. So y equals mx plus c. Instead of m, we have h, which is our constant, and instead of x, we have frequency. And because the gradient is always the same, when you graph out the energy, the lines are always going to be parallel. So in this case, we have potassium and we have magnesium. And so what you can see from this graph is as we increase the frequency, the amount of energy in the electrons will increase. Like that makes sense. As the more frequency you have, the more energy you have. And the more energy you have, the more energy is going to be transferred into the electrons. And yeah, so hopefully that makes sense. Increasing frequency, increasing energy. Cool. And then there's these things. So F0 and F0. F0 is our threshold frequency. Threshold Hz. So what this is telling us is that for potassium, you need at least 5 times 10 to the 14 hertz of light to actually create a current, right? So because everything below this, the electrons don't have enough energy to get displaced. But after your light has more than 5 times 10 to the 14 hertz, photoelectrons are actually going to be emitted. And because of this, the threshold frequency for potassium is 5 times 10 to the 14. So if you want to create a photocurrent, you're going to need light that has more frequency than this. And for magnesium, same thing, but instead of 5, the threshold frequency is 9 times 10 to the 14. So your light has to have more energy than this, or has to have more frequency than this, to actually emit photoelectrons. And yeah, so what we say is that the x-intercept is the threshold frequency. And the y-intercept is the work function. So the amount of energy that you need to actually displace the electrons. And yeah, so putting that together, you get this sort of line, which is just a simple linear line. Cool. If you have any questions so far, put them in the chat below, because yeah, I'll assume that I assume that everyone has a lot of questions about this, because yeah, this stuff gets a bit confusing. But what we can do, we can make things slightly more interesting. So we know that energy is equal to hc divided by lambda. You don't need to know this, but just a little aside. Energy is equal to hc times lambda, but we also know energy is equal to mc squared. And then what you can do is you can split this mc squared into mc times c, divided by is equal to hc divided by lambda. mc, that's basically mass times velocity. Yeah, so mass times velocity, which is also equal to the momentum, p. Yeah, so that combines down to p times c is equal to hc divided by lambda. You cancel out the lambdas, you cancel out the c's, and you're left with this. P is equal to h divided by wavelength. What this tells us is that light actually has momentum. So we have the wavelength, we have some wavelength of light, and that wavelength of light has momentum. Yeah, that wavelength of light has momentum, which kind of doesn't make sense because light is by definition a massless object. And how does that massless object have momentum? That's pretty crazy to think about. But here's where things get even more crazier. What I can do is, so we know momentum is equal to h, which is Planck's constant, divided by wavelength. What I can do is I can switch the momentum and the wavelength. So now we have wavelength is equal to h divided by p. Now, this is the way things start to get interesting. What this is saying is we're saying h divided by momentum is equal to wavelength. And the thing is, everything has momentum. So like this pen in my hand has momentum because it has a mass, has a velocity. So h divided by the momentum of this pen is going to give me the wavelength. Now what we just showed is that mass, or things with mass, or everyday objects actually have a wavelength. And the thing is, you can actually prove it using, again, the double slit experiment. So what some smart people did is, for the double slit experiment, what they did, instead of shooting light through the double slit, they started shooting electrons. So electrons, then they're traveling through these splits. And then, for the sake of time, what they saw an interference pattern, or they saw a diffraction pattern. And again, diffraction pattern, only waves, all waves can diffract. All waves can diffract. So if electrons are passing through the split and they're creating a diffraction pattern, that just proves that electrons have a wavelength. And that's pretty crazy to think about. And the same experiment was conducted on a single split experiment. It's basically the same thing, but when you pass the electrons to the single split, you're gonna get this sort of archery type of pattern, where again, this is a diffraction pattern. So you have constructive interference, deconstructive, constructive, deconstructive. So essentially, we've turned electrons into waves. And again, and because it's a wave, you can apply this sort of ratio where the extent of diffraction is equivalent to the wavelength divided by the width. So if the width of the gap is close to the wavelength of an electron, you're going to see a maximum diffraction. And so this essentially proves that that mass has a wavelength, and this wavelength is called the de Broglie wavelength, because this formula was derived by some guy named de Broglie. And so we get this wavelength is equal to h divided by mv, where mv is just momentum. So now what we're up to is we're saying that light has both momentum. Has a momentum. It's a wave. It's a particle. It's a particle. And now we also show that particles are waves. Particles is also waves, which again is pretty crazy to think about. And what you can do, you can calculate the wavelength of everyday objects. So we can calculate the wavelength of a basketball thrown at this speed. So the wavelength again is equal to h divided by mv, where h is the de Broglie's constant, not de Broglie's constant, is constant. Got his name. It's some guy's constant, which is 6.63 times 10 to the negative 34 divided by mv, which is 0.6 times 5 meters per second, which gives us approximately 2.21 times 10 to the negative 34 meters. Right, so a basketball has a wavelength, and that wavelength is this. Well, the thing is, for everyday objects, this number is just so small that it doesn't matter, right? You can't make a slit that is that small that's going to make the basketball diffract, right? That's just physically impossible. So even though everyday objects have a wavelength, it's just so small that it's pretty much irrelevant. And you can do the same sort of calculation for electrons. And when you do that, you get a wavelength of 121 point, oh, sorry, 1.21 times 10 to the negative 6 meters. Well, yes, it's small. This is in the range of micrometers, and we can actually do things at this size, but this times 10 to the negative 34 is just too small. And yeah, that's why we can create diffraction patterns with electrons. Cool. Hopefully you're still there and your mind is not completely blown just yet, because we're about to get to the most confusing thing, which is special relativity. And this thing, this thing is going to completely cook your mind. So first of all, before we get into special relativity, we need to define what a reference frame is. And reference frame is basically your point of view in the most basic sense. So this person on the ground, he has his own reference frame. This car over here has its own reference frame, and this blue car has its own reference frame. The thing is, from your perspective on the ground, the car is traveling at 45 kilometers, and the blue car is traveling at 50. Yeah, that makes perfect sense. But from the green car's perspective, or the green car's frame of reference, the blue car is only traveling at 5 meters per second, while from the green car's perspective, he's only traveling at 5 meters per second. And because of this, it's a bit difficult to compare the two. Because it's two different reference frames, you can't directly compare like what you're seeing to what the green person in the green car is seeing, because it's going to be two different things. And when you get to really fast speeds, when you get close to the speed of light, things start to get a bit iffy. And inertial reference frame is just a reference frame that is not accelerating. And all three laws of motion will apply. The basic idea behind this is that if you are blindfolded in some dark room, and you're blindfolded in some dark room in some train that is traveling at 100 kilometers an hour, you cannot tell the difference, because again, you have no reference frame. There is no experiment that's going to differentiate whether you're at rest or you're traveling. And yeah, so when you have an inertial frame of reference, it's not accelerating, and every single laws of motion will be the same. Doesn't matter if you're traveling at 0 kilometers an hour or if you're traveling at the speed of light. All three laws of motion will be the same. And what Einstein